Hello and welcome, everyone. As yesterday, we have an audience that is tuning in from all around the world. Today is the second day of our seminar series, and many of you who participated yesterday noticed we were talking about neuromodulation. So that is, we have to read what's going on inside the nervous system, and then we want to manipulate it. And today we are shifting gear. We are going from neuromodulation now to the very important part of brain-machine interface. And we managed to get three outstanding speakers who are really at the forefront of what's being researched these days. Apologies for Dr. Hu Dao, who is tuning in from Shanghai, and it's already very late on his end, but you can see his dedication. It's midnight there, and he's still giving a fantastic presentation. So our first speaker tonight is going to be Hu Dao from the Shanghai Institute of Microsystems and Information Technology. And I heard that you're also the founding director of the X Lab. So you see another one who has a number of hats to wear. And tonight we hear his talk. It's called Silktrode, New Opportunities in Neurotechnologies from an Ancient Material. Just when I read this title, I thought, wow, isn't that fascinating? And you really tuned me in. So the floor is yours, Tiger.
Thank you, Peter, for the nice introduction. Let me start sharing my screen. Can you hear my slides? Okay, it's really a great honor to be here. I mean, virtually to share some of our thinking about brain-computer interface and try to share with you some of our recent progress in making some key components, in this case, neuron probes for brain-computer interfaces. So I have this title. I actually thought about this, how we can try to give you a basic idea about neuron probe, especially enabled by ancient material within 45 minutes. So let's get started. My name is Tiger Tao. You know, Tiger is actually my first name. Hu means in Chinese. So it's nothing to do with my personalities. Okay, so here I would like to break down my presentation in probably a few parts. So I heard that our audience is from all over the world and has different backgrounds. So probably I'm gonna spend a few minutes to just try to give you a basic idea of what brain-computer interfaces are. At least in my own opinion, I try to give you some sense about what are those key components in this brain-computer interfaces. But in this talk, I will mainly focus in introducing the very important component, which are the neuron probes. And also, I would like to show you from some other, probably slightly different angle in terms of how we can use, starting from a materials side, and as an engineer, how we can use this material to try to bring some new functionalities and also some new opportunities to make better, at least in my opinion, better brain-computer interface. Okay, so most of you, I hope you agree. You know, brain is actually the most important organ in human being, but unfortunately, it's the most complex one. So how to say that? Because you know, just by numbers, you know, human brain has nearly 100 billion neurons. Okay, but you know, in a long history of, at least for the Earth, on Earth, probably has a history over like 4 billion years, but our human beings only have like a history of nearly 3 million years. But over a very short time compared to a life of the Earth, 3 million years is pretty short, right? And why human beings, ourselves, as on the top of the, at least on the top of the how to say that, the races, okay, or the species owners, I think it's mostly because of our brain has chosen a right way to evolve into its current form. Not because our bodies or our other parts, because in the nature, that many other animals can have better vision, better hearing abilities, faster speed and more power. But the brain is the most important part to bring us here. However, just because the brain is so complex and is also the most vulnerable organ, so it's extremely soft and sensitive. So, in our lifetime, probably the brain diseases are inevitable, just in different age stage, and at different levels. So I think in this case, as a very important technology, and also as an emerging technology, brain-computer physics has trying to at least give us some hope that we can use this kind of technology try to solve some brain disease problems. Okay, so I just would like to give you a very short definition of brain-computer interfaces. In my own opinion, is basically it serves as a direct communication and a control pathway that is established between the brain and the computer or other electronic devices. So through this pathway, the users or the patients or the doctors can express their thoughts, or they can do some mind control devices as a very simple demonstration. So, however, brain-computer interfaces are very complicated systems. It's not one device; it's a very complicated systems. At least it consists of some kind of electrodes or neuron probes. You can use these neuron probes to read and also to write to the brain, okay? Or in other words, you can record the neural activities, and also you can stimulate or you can modulate the neural activities of brain. And also you need some kind of readout system, readout chip that you can analyze those signals you acquired using this neural probe. Also, you can use this chip to transmit some signal and to write back into the brain. And also you need some decoding and coding algorithms to try to understand what's just going on. What are those signals you just get from the neural probes means, okay? And because you have so many different components, you have to work carefully packaging strategy, try to integrate all these different parts together, especially if you want to use them onto real human being for clinical use. There's many design and fabrication manufacturing rules and also some regulations you have to follow. So because as an engineer, our goal is trying to build better tools for two kinds of users. A is our neuroscientists. They need a better tool to understand what's going on in the brain, how we can understand better, how we can modulate better, mostly for the animal models. That's one large part of users we're trying to serve for. And another part of the group of users, of course, are neurosurgeons. Okay, they just need better medical devices they try to use to cure these brain diseases. So if you can take a very brief, history in the past probably 10 to 15 years, there are many pretty good progress, and I would rather call it breakthroughs in this brain-computer interfaces. For example, there's some new tools to combine optical functions with electric functions, which people use it as so-called optogenetics to try to modulate the brain activities, okay, neural activities. And also there's some product of medical devices that are already being used for clinical use or at least clinical trials. For example, we may know the Utah arrays. Okay, I believe this is still the only one has got FDA approved and has been tested on probably nearly 40 patients in the past 20 years. And also in recent years, there's some exciting technology that we know from Elon Musk. He built up this Neuralink company to try to use this high throughput, high count channels, flexible electrodes, and try to do some very fancy work. I believe just in last year, they were able to show using this kind of technology to use on a monkey to try to play video games, or even though the video game is pretty easy for people. So still, if you take a look at this, those progress are quite exciting. But if we take a look at this, I believe as in my group, we basically focus on two key parts. The first one is those neural probes. If you can just divide them into 3 different categories by where you put them, right? You can divide them to get this EEG electrodes, ECOG electrodes, and some SEG implanted ones. So as you can see very clear from this very simple cartoon here, if you go deeper into the brain, of course, you get better signals and you can modulate more precisely. However, you're gonna get more damage to the brain. And so in our opinion, in order to try to have a balance, or I can go back a little bit, if you want to have better performance of these neuron probes as part of this brain-computer interface, you really want to go inside of the brain. That's going to cause some other issues, especially some damage to the brain. So in our group, we have been struggling with, or we have been working on the key challenge, we think, in building better brain-computer interface. We have been thinking of this every day is how to maximize the performance of these neuron probes while minimize the damage to the brain. So as many circumstances, we have to do a lot of trade-offs. We have to compromise one part for the other. But still, we think that those implanted ones, those deep implanted neural probes can give us better performance. So what we are trying to do is how we can try to reduce or try to minimize the damage to the brain in terms of the electrodes themselves, and also we try to pay attention to the long-term or the chronic stability of those probes. Okay, so this is a slide I borrowed from the speaker from yesterday, Professor Hong. They have a very nice review paper trying to explain what is going on. If you have this implantable probes inserted in the brain, so how they can interact with these neurons, and what kind of damage, what kind of immune responses you're gonna get with different format of these probes and with different materials. But one thing is pretty straightforward, right? Because our brain is very soft, and most of those probes you can get from commercial companies, or many people they build in their own lab are pretty rigid, either from metallic probes or some silicon-based. They are all rigid substrate. So those rigid probes, if they were implanted into the brain, it's gonna cause pretty severe immune response to the brain, and so that it's gonna cause some scar, and those scars gonna cover the surface of this electrodes, and it's gonna reduce the performance of their those probes, because they cannot read or cannot write the signals very good after some time of implantation. Of course, there's some tricks you can play, right? If you already choose one material to build those probes, the Young's modulus, this intrinsic properties of this material is set. Okay, for example, if you decide you're going to go with silicon, okay, the Young's modulus silicon is very high, as you can see, it's up here. Of course, if you want to make this probe softer, there are many ways you can try, but there are probably 2 major strategies. One, you can choose softer materials. You can use probably some kind of softer metal, for example, gold, or you can just go for a polymer or even hydrogels made of polymer. But as you can see, they're still pretty hard if you can compare the Young's modulus of these materials to our brain. But the Young's modulus is not the only thing determining how bad it's going to cause in terms of immune response of those probes. There's another thing, in my own opinion, probably even more important, is the bending stiffness, or in other way, or in a very simple way to explain this is how soft they are. So this is very simple equation. You can understand here. The K is the bending stiffness, E is the Young's modulus. You know, if you already choose a material, this one is set, but the bending stiffness is proportional to the T to the third, T is thickness here, which means if you can reduce the thickness, then you can reduce the bending stiffness a lot. For example, if you reduce the thickness by a factor of 10, you can actually reduce the bending stiffness by a factor of 1,000, which means with the same materials, just with a thinner format of this neuron probe, then it can have 1,000 times softer or more flexible if you do a simple math. Okay, so that's why in this brain-computer interface, especially for people who are trying to build better neuron probes, many of them have tried to use soft neuron probes. Okay, how to make it softer? Simply make it thinner. So that's in terms of how you can choose the right materials and how you can probably try to improve their the performance in terms of reduce the bending stiffness by simply reducing the thickness. Okay. Additionally, people have tried to increase the density of electrodes. Okay, which means how many channels, how many electrodes you can build, you can integrate into one single device and try to do either a neuron recording or neuron stimulation. And also people really want to have those long-term recording or long-term stimulating electrodes because there's many brain functions you want to study actually rely on the long-term or the chronic performance. So these two things are pretty important, are very much designed for all researchers who are trying to build better electrodes. Of course, people are also trying to build multifunctional electrodes. In this case, you want to, add some optical functions into that. Also, you probably want to add some ultrasonic functionality into that. You want to make it MRI compatible, and also you probably want to do some drug delivery along with this electric or optical stimulation. Okay, so I hope I already give you a basic idea in this field how we're trying to identify those key challenges and what are those general strategies we're trying to use to make better neuron probes. Okay, so already told you, for those neuron probes, there are basically three key challenges here, or three key problems with current or most of current probes. Of course, again, the channels number or the number of channels pretty low. In the past 60 years, people have successfully tried to increase the channel from 3 to nearly over 1,000. But it's still pretty slow, compared to semiconductor devices, right? Nowadays, because my background is IC, is for those sensors and the chips. So in my field, it's pretty easy to integrate the millions, if not more, transistors or devices into one tiny devices. Okay, so we would like to adopt that kind of strategy, either design or fabrication strategy, and apply that to making neuron probes. Why it was pretty slow to build high throughput electrodes? Because one reason is in the past, probably 50 years, people still trying to build this neuron probes as a medical device. So people have, even in my lab, we still try to make this microwire bundle, either 4 microwires, 8 or 16 as a maximum together by hand. Of course, it's maybe enough for some very basic testing for small animals, but if you want to do some advanced function exploration, you need high throughput. So in this case, we need to at least think another way. In this case, we're trying to use semiconductor manufacturing strategies to try to bring up the channel numbers rapidly. And another thing is for this implantable neuron probes, of course, you have to consider the damage. due to the surgery, right? This I just borrowed some pictures from these two very famous cases. For this one, this is Utah array. As you can see, it has 100 electrodes, and each electrode is connecting to a thin flexible cable, and this is trying to do the IO cable, right? As you can see here, of course, they can slightly increase the number of these electrodes, but just due to the configuration of this kind of design, it's really hard to make it as, for example, 1,000 electrodes. It's really hard to do that because it's really hard to try to have 1,000 connecting cables out like this. Another thing is, if you want to insert or you implant this kind of device into the brain, you have to open up an opening in the skull. Okay, so in this case, you have a risk of have a large opening in the skull, and it's going to cause some kind of infection, and also it's also some extra damage to the brain. These are rigid probes. These are flexible probes. I think this is the surgical robot built by Neuralink. The idea here is, flexible probes are designed, but those flexible probes are too soft to be implanted by themselves. You have to use some kind of, we call it shadow device. Okay, shadow device. You have to attach this flexible cable to this very hard, very rigid, very strong shadow device so that you can insert that flexible probe into the brain, and then you release the probe and you retract the shadow device. The same problems remain. You still need to open up the skull so you have access to the implantation, and also because this shadow device is pretty rigid, it's also going to cause some damage to the brain. As you can see here, you have many tiny holes here. Okay, so this is for the electrode probes themselves and the implantation technique itself. And also one thing that's very important is the long-term stability. As you can see here, if you insert or you implant a rigid probe into the brain, because it's so rigid, okay, and also just due to any kind of relative movement between this rigid probe and the brain itself, it looks like, and it's actually the probe is cutting the brain locally, and it's going to cause immune response. So that is going to have some scar formed on the probe, and it's going to cover the probe, and it's going to lose its electric signal. Okay, so these are three major challenges we are facing. So let's think how we can try to solve them, at least some partially. So in this case, we think, of course, you want to have better design, you want better manufacturing strategy. And here we decided we're going to go for material first. We want a better material in terms, we want it's more biocompatible. We don't really want any like metals or at least this kind of like or synthetic polymers. We really want to use a better biopolymer here so that it can have better biocompatibility. It can stay longer in the brain after implantation. And also we want this material is quite strong, mechanically strong. So in that case, we can make it thin enough, but still strong enough to hold the device together. As I just mentioned, make it thinner is better. Of course, if we forget about electrical performance for now, if you make it thinner, it's gonna better in terms of its cost, less immune response and have better long-term performance. But if you make it thinner, you have to make sure the material itself is strong enough to be so thin. Okay, and also this are basically two starting point for us to choose the right material. And later on, I'm going to show you why we choose silk as this material. And there's some other attributes we can get from using silk, in addition to be a very good biocompatible material and a very strong material. Okay, so I'm going to shift the gear a little bit to give you some idea of silk. Because I'm from China and silk, we are very familiar with silk, and silk is indeed an ancient material of over at least 5,000 years history. But in the past 5,000 years, people have mostly used silk as a textile material, for this fabric, either make it into a tie, a t-shirt, a scarf, and so on. So what they do is they try to extract the fiber from the silk cocoon and weave that into the fabric. We just do it oppositely, okay? Instead of weaving that into a fabric, and we just dissolve it, and we extract the protein from the fiber and turn it into a silk solution. So this is the starting material of everything we have been building. For example, in this case, a Silktrode. Okay, so this is the silk protein solution, and we're using this silk protein as a medical implants, as a biopolymer-based optical device, a photonic device, electronic device, and in this case, a neuron probe. Okay, let me show you what kind of format we can get, because one beauty of using silk is it has different material formats. For example, itself is a fiber, and once we dissolve them and we extract the protein and its solution. Okay, just by some manufacturing techniques here, we can either turn it into a very flexible film as a supporting substrate of the neuron probe, and also the packaging material of the probe. And also we can make it into a very hard block. So it had different formats. And as a protein, as it has extra beauty, is biodegradable. Okay, and then we can precisely control the degradation rate of this material. For example, we have this two little piece of silk film. We just dope that with some green foot dye so you can see it better. Okay, so we have this. They originally from the same big piece. Okay, we just did some different processing technique here to try to modify the degradation rate. For the top panel here, we program it to dissolve in PBS very fast. As you can see, once we drop that into PBS solution, the film is going to dissolve, and everything you embedded into this film, for example, any drugs, is going to release, so it's control the drug delivery. But for the bottom panel, we do some post-processing technique to increase the cross-linking degree within this film, as you can see, stay intact. Okay, we can control the degradation rate from a few seconds to a few weeks and longer. So that's one properties we're going to use for building our silk probes. Okay, and also it's compatible with this micro nano manufacturing process, because nowadays, because we're using micro nanotechnologies to make this high throughput tiny neuron probes. So we want to make sure this material, this biopolymer, this natural protein can be compatible with our conventional microfabrication manufacturing techniques here. So I won't go through them all, but as you can see, you can either make that into a film, or you can just load this solution into a commercial inkjet printer, and you can print those devices. Or you can make that into a film, and you can build all your electronic devices on this film and turn it into a silk-based flexible electronics. Okay, I'm just gonna show you one example here. This is an optical fiber we printed using silk as a material. So these are silk fibers. It can propagate in light, and it's very flexible and it's biocompatible, and it can programmably degrade inside the body. So we can use some of these properties for our optical genetics applications. Okay, in addition to that, you can also very easy to functionalize it. For example, you can simply mix this solution with other functional dopants. For example, you can mix this with laser dyes. You can have better light properties. You can mix this with quantum dots, with nanoparticles. You can make it have some plasmonic response. You can make it conductive and so on. And on the other hand, you can also mix this solution with antibodies, drugs. You can mix that with enzymes, vaccines, okay, and it can turn it into a therapeutic device. And all this we're going to use to build better neuron probes. Okay, so this is why we call it a Silktrode. Is actually we combine the beauties of silk and the electrodes for making the Silktrodes for better neuron probes. Okay, so I'm going to just show you some examples. So we built two different kinds of electrodes. This is people were familiar. This is we call ECOG electrodes. Okay, it's just gonna apply it on the surface of brain. As you can see, we have pretty high electrodes count here, we can integrate over 500 electrodes on one tiny piece, and it's very thin, it's only 10 micron thick. So as you can see, it can very nicely conform to the curved surface of brain, so it have better signal-to-noise ratio, and it can do better in terms of the neural modulation. And also these are deep brain electrodes, this implanted ones. So we fabricated that on some silicon wafer, and we released them from the wafer. And as you can see, this is a zoom in picture of those probes. It's very flexible, and we have highly integrated electrodes on each shank, and you can design how many shanks you want to have in terms of how large of brain area you want to cover and how many electrodes on each shank. And also, in order to have those signals nicely read out, you need to have this high density package to connect to this electrodes, okay? And for this one, we make them even thinner. We can make that 1 micro thick so that it can cause very little, damage to the brain after implantation. And also, we build some readout chips to be compatible to those high throughput electrodes, and also some readout equipment here. Okay, I won't explain too much on this. Okay, so in this case, you can have those silk as supporting layer and also the encapsulation layer. Okay, so this can enhance the strength of this very thin, flexible probe. And in additionally, you can dope this either supporting layer or the packaging layer with bi-dopants, for example, antibiotics. So after you implant this neuron probe into the brain, those packaging materials are going to get degrade, and those drugs are going to get released, and then we can control the releasing rate. Okay, so for the rest of the seminar, I'm going to go through 3 examples. Some of them are very recent results. So I'm going to divide them into 3 different categories. One is shadow-assisted silk-glued ultra-flexible neuron probe. So in this case, we just make those flexible, thin neuron probes, okay, with standard IC fabrication process. Okay, as you can see, we can make from hundreds to thousands of electrodes within one single device here. As it's very thin, as can increase the working life time after implantation. And here comes a problem, because it's very thin and flexible, so it cannot be strong enough to be implanted by itself. Okay, so we have to try to attach the SIM probes to some kind of rigid shadow device so that you can use this together to do the implantation, okay? So in this case, we just use tungsten wire here. I think many other groups have using a similar strategy to do that. But in this case, silk only serves as a very small part here. We only use silk as a glue here to serve as a temporary glue to glue this flexible probe to this rigid tungsten wire so that it can be strong enough to be implanted into the brain. And after it's implanted, okay, the screw is gonna dissolve, and we can retrieve the tungsten wire, and this flexible probe is gonna stay inside the brain. It's very simple. So in this case, silk is only served as a temporary glue here, just for implantation. Okay, of course, we can make it into pretty small footprint here. As you can see, we can have the weight is only 2 grams and it's very small, and we did that on small animals. The thickness is only 1 micron here. Okay, so we tested on some small animal models, and it's turned out to be pretty nice in terms of the acute response. We can actually get pretty nice signal, including local field potential and the spike signal, within only 5 minutes of implantation. And just because the probes themselves are so flexible, it can cause very little immune response to the brain. So it's going to have pretty good long-term performance for a chronic recording. So we have been successfully record typical neural activities over 8 months. Okay, so that's pretty good in terms of implanted neuron probes. Okay, so of course, using this probe, you can also do some neuromodulation because same electrodes can do recording and also stimulation. Just because those electrodes are so tiny and you are using much lower current to stimulate that compared to commercial DBS device. So in this case, for the electrical stimulation, we can also make it pretty long-term lifetime in terms of chronic performance. Okay, I will not spend too much time on this part. I really want to go through the next two probes, which can use better in terms of all the beauties of silk. So next one I would like to introduce is the shuttle-free silk-based ultra-flexible neuron probe. So in this case, sorry for the Chinese characters, I didn't have time to fix that. But as I just mentioned in the previous slides, as you can see, this is the neuron link technology. It's pretty neat. Okay, they have this shadow device to try to insert this flexible probes into the brain, and also you can insert multiple probes automatically. But as you can see, they have to open up an entire window in the skull so that they can insert all these probes using this kind of technology. So as you can see, if you want to do this, you may need to open up a centimeter size, if not bigger. I don't think that is a very good strategy to promote this technology for more applications. So in our case, we try to avoid that. We avoid using any rigid part here. So in this case, we just use silk as the temporarily coating layer. So we just coat this neuron probe, this thing only 1 micron thick neuron probes with silk coatings, with silk layers. So we tune the mechanical properties of this coated device to be harder enough so that they can be implanted, but make it soft enough, it won't damage the blood vessel. So the main reason why they need to open up this window, because they need to see where the blood vessels are so that they can avoid this. But in this case, we can finely tune the mechanic properties of the silk-coated flexible probe so that is nicely between the very soft brain tissue and the slightly harder blood vessel. So in this case, we only need to open up a very tiny hole. It's only bigger than this probe itself. In this case, it's sub-millimeters. In this case, we only open up a 0.5 millimeter hole. We can do that, okay, regardless if there's a blood vessel or not right in this implantation site, okay? So let me show you a very simple animation. So this is the typical rigid probe, for example, Utah array. Okay, so if you insert that, it's going to cause some damage. This is the shadow device assisted. Still, if you retrieve that, okay, it's going to have some displacement. But if you use the silk-coated flexible cable here, okay, it can be self-implanted. Okay, so in this case, if you compare the technology of, for example, neuron link and other technologies here, and if they do this very hard shadow device is gonna, if they encounter to the blood vessel, it's gonna cause the bleeding. But in our case, even it's gonna directly contact with the blood vessel because it's soft enough, it's gonna bypass the blood vessel and get inserted into that. So in this case, we do not need to know where the blood vessels are. We can just simply implant those neuron probes where they should be. Okay, so we did some animal experiments and in vitro experiments. This is probably can show you better, right? So this is for the rigid shadow device. It's gonna even slightly scratch the blood vessel is gonna cause the bleeding due to the breakage. And if you have this Silktrode, okay, if it's gonna encounter the blood vessel, it's gonna slide over to that. This is the simulation here, okay? And we have some microfluidic channel just to mimic the blood vessel. And this is our Silktrode. As you can see, we just aim this Silktrode to this tiny pipe, which has similar mechanical properties of the blood vessel. it can slide over, but if you just use a hard, it's rigid shadow device, it's gonna pierce the blood vessel and it's gonna cause bleeding. And this is what we do. We actually test that on the brain of I think it's a mouse. We just directly aim this device to the vein of the one vein here, as you can see. We just, before we get contact, we insert and recheck. There's no bleeding. By the way, this is not blood bleeding. This is just some tissue fluid here, okay? And let me show you some video here. And as you can see, we only need to open up a very tiny hole, and then we just directly do that. And in comparison to other technology, it has to locate where they want to do the implantation. This area has to be no blood vessel around. Okay. Another advantage to use this is, as you can see here, if you're gonna use a shadow device to do this, usually you're gonna see a challenge here. Sorry for the back and forth. So what you're gonna see here is, after you recheck the shadow device, there usually gonna be a displacement of the flexible neural probes just due to the retrieval of the rigid shadow device. So there's gonna have some displacement. Okay, so with different retrieval technology, it's gonna have some kind of sub-millimeter or even millimeter size of displacement. So which means you can never get a very precise implantation, especially for the Z direction, for the depth here. But for the Silktrode, because there's no retrieval process at all, so after you implant this Silktrode, the coating is going to get dissolved and degrade inside the brain, and the byproduct of the silk is only amino acids. Okay, it's totally safe for the brain, and it won't cause any displacement of those electrodes. So you're going to have very precise implantation site here. Wherever you implant, it's going to stay there. So that's another advantage you can get from using this very simple strategy. Okay, you can just use this biocompatible silk as a coating device and just tune the mechanical properties between soft brain tissue and hard, blood vessel. You can just do that, and it's going to also, cause much less challenge to the surgical robots. Okay, so in this case, you just need a very simple robotic arm which can pick up this probe and just do implantation. Okay. So, and also you can very easy to make that in array form. You can either insert one or a line of this probes and also array of that. Okay, each one you can coat silk, and you can do that. This is just another version of Utah array, but you have silk coated and they're flexible and they have much higher channels compared to Utah array, and also they can show pretty nice, chronic performance. So that's the second part I want to introduce to you today. And also we try to on different animal models, on small animals and some kind of non-human primates here, it's still pretty nice results. Okay, the last part, I think I only have a few minutes left. So the last part, I want to quickly go through another multifunctional neural probes we're using silk as a key component here. So in this case, we can also make a flexible silk optical fiber, and we attach this flexible neural probes to this flexible silk optical fiber together. And again, we just tune the mechanical properties of this flexible silk optical fiber to be able to be implanted by itself, and also, to avoid this bleeding stuff. As you can see here, these tiny dots are electrodes, and this are the optical silk fiber here. And the silk optical fiber can propagate in light, and those flexible neural probes can be nicely integrated, wrapped around this optical fiber, and to be implanted together. Okay, so I would skip this part, how we make this optical fiber, but it's pretty straightforward. We have another paper to introduce how we make this, but the result is shown here. Okay, this is a optical fiber made of silk only. it's pretty smooth and it's pretty flexible, and we can make it long enough to be implanted into the brain. And we tried it on a brain fountain here, and it can propagate light nicely. And we integrate that with a flexible neural probe and with some kind of a head stage, and insert that into the brain of a mouse. Okay, here's some results. Okay, we just implant that, and we have the stimulation of light, and we try to monitor the electric signal here. We can see a very nice response of the electric signal due to this light modulation here. Okay, so this is a close-up look here. So you have this optical fiber here, and you have this electrical part here, and we can just stimulate by light into certain area of the brain, we can control the movement. In this case, we just make the mouse do circles here. Okay, and also just due to the flexible nature of its very thin neural probe, so it can stay functional after implantation for really long time. In this case, months. So it can allow us to do more advanced study of this device and also brain function. Okay, so I would like to summarize our goal here by to see what we want to do. Of course, all these are on animal models. We already tried test the safety issues and the regulation issues of those kind of technology. And the next step, we're going to try it on human trials. So idea here is going to try to, for ALS patient, we can try to use the Silktrode as the implanted neuron probe and combined with other, neuron chips and some robotic arms and some decoding encoding algorithm built into a BCI, brain computer interface system for language synthesize and also for mind control movement here. Okay, we're working on it right now. I hope I can have another opportunity to show you if we get some other results. So I'm going to stop here trying to summarize what we are trying to build up here in terms of technology skills tree. So of course, we build our technology trees on electrodes here by using silk as a very nice materials to make better probes. And of course, we are trying to build up our skills on chips, so which can be integrated, which can be compatible with those new probes. And also with those new probes, we have been building a surgical robot for this. And believe me, those surgical robots are going to be much easier to be built. You can simply modify a very simple, very easy available surgical robot. Just do a very simple modification, which can be used to be compatible to those electrodes. Okay, and of course we're going to working on this algorithm and the database. Okay, so I'm going to stop here and thank you very much for your time, and I'm happy to take any questions. Thank you.
Thank you, Tiger. This is a most fascinating presentation. I have to admit that I had no idea that you could do this with silk. For me, silk is just a kind of flexible material that you use for wearing all sorts of, be it shirts or scarves or what have you not. But this opens up a completely new avenue. This is most fascinating. And as I can see, you're probably only at the beginning of this process. So in 10 years from now, we will see a lot of other devices, I hope.
Thank you.
In the meantime, our audience has started asking some questions. And the first one here is, what are the technologies you are using to fabricate such sophisticated and robust probes?
Okay, I also noticed from the Q&A panel. So this is very good question. So I'm trying to expand that in very simple words. So for those Silktrodes, they basically consist of two most important parts. One is the flexible neural probe itself. Okay, it's only 1 micron thick. So in this case, we just use standard microfabrication technology for example, lithography, deposition, etching, and coating on a standard silicon wafer. And after we make those flexible substrates, we just release them from the supporting substrate, and they remain flexible. So that's how we make those new flexible neural probe. But in order to make sure you can use them, for example, to be able to be implanted in the brain, so here we're going to use silk as either supporting sub layer or the encapsulation sub layer or the coating layer. Especially for the second part of the Silktrode, the coating layer, we simply just dip this flexible neural probe into a silk solution, and by control the concentration of the silk solution and how long you're gonna stay, you're gonna have the probe stay in the solution, and how fast you're gonna pull up the probe from the silk solution, you can roughly control the thickness of the coating, and then you do some post-processing try to adjust the cross-linking degree within the silk coating layer, and then you can adjust the mechanical properties and the degradation rate. And if you want to do some more fancy function into that, for example, you want to embed some drugs. In our case, we also do some antibiotics into the coating. Then we just mix these antibiotics drugs in the silk solution, and then these drugs are gonna be embedded into the coating. And then once you implant that into the brain, those silk coating gonna dissolve, and this drug is gonna get released. So that's pretty easy to do. And for the third part, the flexible silk optical fiber, and then you can do it also very easily. So you can just have this silk solution into a syringe and get a pump, and you can just squeeze the solution into a very tiny hole of the needle, and it's gonna form a fiber by itself. And that's basically how we do it. Of course, we have some know-hows to make a smoother surface with better light optical properties. And we're gonna have a paper coming up pretty soon, and I hope I can share with you that in the near future. Thank you.
Super. The next two questions are related, and they have to do with displacement. You mentioned that there's minimal displacement of the Silktrode compared to a typical traditional electrode. But you also mentioned that the Silktrode can bypass the blood vessels. That was quite impressive. But wouldn't this imply that by bypassing the blood vessels, the Silktrode is being displaced from the target side?
Yeah, I think there are two questions, right? So basically, one is compared to typical MET electrodes, if there's a significant improvement in terms of displacement. And the second question is, if you bypass blood vessels, it goes right straight down, or it's gonna, go to a slightly different angle, right? So, for the first question, compared to the metallic electrodes, any flexible probe is gonna show better, because what we really care is the relative location or the relative displacements between the probe and the brain. But as you all know, our brain is soft, and our brain is moving all the time, with respect to our skull, right? So if the metallic probe, which is usually fixed to the skull, is fixed, then while our brain is moving, there is going to have a relative displacements between the rigid and fixed metallic electrode and the brain. But for those flexible ones, especially for the ultra flexible ones, because they're flexible enough, their bending stiffness is so low, and the softer probe is going to move along with the brain. So there's very little displacement, relative displacement between the flexible probe and the brain. So that's why it's going to show better in terms of the signal, recorded signal, and also long-term stability. So that's one thing. Another thing in terms of what we have tried to use this Silktrode directly aim to the blood vessel, and we can see it's going to bypass the vessel and continue deeper into the brain along with the path. I cannot give you an exact answer. If there's a slightly, away from the from the past. But from what we can see here, we don't really see a huge angle of away from the designed past. So that's one thing. Another thing is, even there's a slightly away from the past, I don't think that's quite a matter, because for many applications, it's really about what kind of brain region you're going to implant that your flexible cable into. And I also noticed if there's another question is, damage the veins as well the arteries. I don't think that's a problem, because there's a huge range we can play with the mechanical properties of veins and arteries as against to the very soft brain tissues. So we can nicely design the mechanical properties of the Silktrode according to different animal models. So I don't think that's going to be a problem. Thank you.
Yeah, maybe you can continue with these questions on longevity. You recorded up to 8 months.
Oh, okay, yeah. So 8 months. That was an old slide. Actually, we were able to manage to see it's working over 1 year. It's basically the lifetime of a mouse, right? Because the relative lifetime of mouse is roughly over 1 year. So we can actually see the entire lifetime of that. So but for some cases, just due to some implantation issues or the animal conditions not that good, we do see the signal decreases after a few months, even sometimes after a few weeks. Basically, what you're going to see is you're going to slightly lose the signal loss ratio to on those recorded channels, and also later on you're going to lose those channels at all. So that's what we're going to see. Yes, diminished signal.
Along the same lines, there is here another question asking about what is the age when you implant, and does it make a difference if you implant in very young animals when the tissue is perhaps softer, or if you implant at a later stage?
We mostly deal with those animals with the very young age. Yes.
Yeah. So can you give us some age range what you're using at the moment?
I'm sorry?
What is the age range that you're using at the moment?
At this moment, I think it's, a few weeks or 1 to 2 months at most. Yeah.
Okay. Thank you very much.
Thank you.
This was the most enlightening talk. And thank you also, like our speakers yesterday, you managed to be bang on time, exactly 1 hour. And I can see that our next speaker is already waiting. So it's getting late on your end, so you deserve a bit of rest now. Thanks very much from every one of us. And I hope to see you again in the near future.
Thank you.
So in the meantime, I can see that Stanisa has gone live. So let's hope that everything works fine. Yeah, oh, that looks very good. So our next speaker is Stanisa Raspopovic, and he is from the neuroengineering lab in Zürich in Switzerland. And he is talking about nerve-machine interfaces for neurorehabilitation. So, Stanisa, it's all yours.
Thank you. It's a great pleasure to be here. And yeah, it's also becoming late in Europe. So I'm going to try to make it in time for European dinner time. So I'm more than happy to be in this crew, which was mainly speaking about the brain issues. So we're going to jump a little bit downstream and speak about a peripheral nervous system in this presentation. And more in particular, I'm going to engage with a few examples of our usage of neuromodulation system for both invasive and non-invasive stimulation of the nerves for the health benefits, with more translational aspects. So starting from, I would like to start from our research vision, which is making a translation between basic science and clinics. So in our lab, we are starting with understanding the mechanisms of touch and multisensory integration. And to do so, we do have tools that are multimodal tools, both for measurement and manipulation, for instance, of the multisensory integration. Then we do work also about the body representation, so the body landmarks or foraging body sensations, or the way that we are quantitatively measuring so-called embodiment, which is meant to be used for tomorrow therapeutic solution. I'm going to explain a few details about that likewise. We work a lot on a personalized digital health regarding the health of the pain treatment, and I'm not going to speak about that today. And we do work with the damaged nerves, and you're going to see a lot about that today. And also, we do a lot of computational modeling in order to simulate the neural activity, so to understand in silico the behavior of the implants we're performing into the nervous system in order to make an optimized bioelectronic medicine treatment. And last but not the least, and that is the majority of this presentation, we do work on artificial restoration of the sensory motor function in order to enable the better, the more optimized, personalized human-machine interfacing. So what are the specific challenges in this multidisciplinary research field? So we are trying to deal with a clinical unmet need of specifically aging populations such as diabetics, strokes, or amputees. And this is the way that a severe diabetic patient is working. Those persons are having low mobility, they are suffering falls, they're having pain, those with stroke are having grasping problems, or those with upper limb amputation. And last but not the least, and that's very much important to our health system, they're having the loss of independence. The way that we try to approach those problems is to communication with the nervous system, with the residual healthy nervous system. So we are engineering the devices, both the type of device and the way how do we speak to the nervous system. So indeed, we try to understand through our modeling and animal experimentation which and how nerves should be implanted. And then we also learn how to speak to the nerves. So we are trying to engage into the best, most optimal policies of the stimulation. And to do so, we are really making the neurotechnological solution. So to do so, we are implanting into the upper and lower limb, even close to the spinal cord. And we are engaging the merging of different neurotechnological technologies in order to make the most suitable targeted solution for a specific category of patients. And to be optimally good in doing so, we must think about surgical and technological viability. So we must do a proper animal and cadaver experiments. And if all of that is done in a proper and optimized way, then we are able to eventually restore the lost sensory motor function or to make the pain management in those categories of patients. So to do so, we have a research philosophy which is starting from a basic knowledge. So we start from deep understanding of the system. So in this particular example, you can see the human histologies on the left. And so we do this in silico models of those, plus some of the mechanoreceptors you're going to see in 3 seconds from now. And then we make models that are enabling us to learn how those systems would respond to the external electrical current. Then we do construct the devices. We really do on the mechatronic devices development. And finally, we go to the clinic. We do the clinical validation and assessment. We try to understand what are dynamics, kinematics, or metabolic benefits to categories of patients I've been mentioning. But the real advancement of the science is happening in the last step. So when we are in the clinics, when we learn about our system and we learn what was right and wrong in our basic hypothesis, and then we feedback that knowledge into the basic knowledge. And this is where we push the science forward. So we understand what was wrong in order to make a better science of tomorrow, and then iteratively ameliorate this approach and therefore the health of the patients. So to start on this journey, I will give you a flavor of what I'm speaking about. So all of us, when we think about amputation or diabetes or stroke, we typically think about the movement, and we rarely think about the importance of the haptic feedback. But if you think about your hand, like playing the guitar or trying to grasp in a proper way an apple, these are the actions where the sensory feedback is crucial. And in a specific historical example, as the one from the Johansson, you can see here the example of the simple experiment in which they anesthetize the fingertips, in the case on the right, And they're trying to do the same action, which was already finished on the left. So the person having a sensory feedback is able to manipulate the fine movement very easily, while the person on the right with anesthetized fingertips is yet trying to do it. And I've been speaking for quite a while, but she's yet not managing. And finally, the same person on the left managed to do it on the right with anesthesia with so much more time. So you are able to do the things, but it costs a lot of effort, a lot of energy. These are the actions that then are not easily integrated and accepted by the users. So in a case of amputation or diabetes, it's super important to give back this type of sensory feedback. And to do so, as I've been describing in our philosophical approach, we need to understand how to speak to the nerves. To do so, we first want to understand which is the language of natural receptors. And in reality, we developed quite detailed computational models that are taking into the account the realistic mechanistic behavior of different areas of the foot sole, their hardnesses, for instance, and connected that to the behavior of different mechanoreceptors that are happening to exist there, like FA12 or SA12. Then we did a specific experiments in which, in collaboration with the Canada collaborators, in which they've been measuring the regulated pressure over different areas of the foot sole, and then via microneurography, the responses of the single afferents. And we were able to make a model that is quite realistically resembling the behavior of these different afferent classes when those are applied with the external mechanical stimuli. Then the next step was to exploit such a model into development of biomimetic patterns. What does it mean? If you imagine a user that is missing a leg, and then we really want to speak with the proximal nerves in most biomimetic possible way, we use that model to emulate the mechanical stimuli over different areas of the foot sole with a realistic behavior, and then to make an artificial code that is resembling the behavior of different spiking afferents, which would reply in a proper way if those were untucked. And then, of course, what we wanted to do is to make one-to-one encoding into our neurostimulating system, in which we would really make as similar as possible the way that we are injecting the artificial current into the human nervous system. Then, of course, the next step was to test those things in animals. We were lucky enough to have a great animal collaborators that helped us to make a unique experimental setup in which we are able to stimulate the peripheral nerve and then to record both on the level of dorsal root ganglions and of the spinal cord in per se. And we were able to see in this oversimplified explanation that the signals which we are injecting in the periphery, the way that we are stimulating biomimetically like in the periphery, is being conserved on a different levels of recording. So in dorsal root ganglion or on the level of the L6 neural response in the spinal cord. That makes us believe that what we are doing is quite resemblable to the natural activity. If instead similar graph is presented as with a constant frequency stimulation, for instance, that information is not being transmitted in the proper way to the nervous system. So this asynchronicity, which was imposed by our biomimetic encoding, makes sense to make more plausible, more realistic signals. Of course, we can't ask cats about what do they feel when we stimulate them. So the next step was to make as I promised, the mechatronic solution, so the sensory neuroprosthetic for amputees. And so this is the way that amputees are walking. They are asymmetric, quite slow and unconfident. So we equipped a prosthetic device with a sensorized insole and encoder into the knee of the prosthesis. And those artificial signals are wirelessly transmitted to the brain of the system, which at its turn is triggering the implanted electrodes, which were properly designed, as I was mentioning. And the encoding is done similarly as biomimetic as we were mentioning. Then those signals are transmitted through the residual nerves, then the nature does the rest. The signal is conveyed through the spinal cord until the brain, and users are able to adapt the walking as having back again their leg that they've been missing for several years. Okay, that's a nice simulation, but what happens into the reality? So in reality, we performed the implants in collaboration with our multiple clinical and industrial collaborators into the proximal section of the tibial nerve on a tile level in the highly disabled transfemoral above knee amputees. And then we took care also about a very important neurotechnological issue. I've been mentioning those, which is the proper fixation of the cable. So those electrodes are so small that we were almost more afraid that the big muscles in the leg are going to break the electrodes, rather that with respect to that we are doing some damage, because we properly tested those electrodes. And after a while, we could have those quite stable electrodes with transcutaneous connection for up to 100 days in 3 different subjects. We performed this study with several research and technological partners involved. And after very few days after implantation, we were able to jump in and to make the mapping procedures to understand what are we doing? Are we giving any benefits to those users? And so this is what happened. All of those users were multiple years amputees, above knee amputees, and 3 legs would represent what 3 of them were feeling, and different colors are responding to the different neural implants. So we've been giving several neural implants within the tibial nerve. And as you can see, we were able to give multiple redundant sensations over the foot sole and a lower leg. And then those users were able to feel those very reliably and quite naturally. And so when this is intrinnsically connected to that type of sensorized install, this is what happened. This was a placebo trial. So what's happening, this blue sensorized insult through this green box, it's transmitting the artificial signals while I'm pressuring it to the white box on the table, which is a neurostimulator, which is through the cables you can see transcutaneously stimulating the residual nerves, and user is able to feel the leg as it being again part of his body. Of course, we ask ourselves, what is happening with the brain while we are doing so? To do that, we did 2 types of tests. In the first one, which is the upper figure, we were moving the pool that you can see while the user was not able to see his artificial leg. And then we were asking in which moment did he feel the leg aligned with his hallux. And basically, we were able to experimentally measure the alignment with his sensation post-stimulation with respect to what we were able to have with only commercial device. Together with that, we also did a lot of standardized questionnaires. And long story very short, those users were able to perceive prosthesis as being more part of their body, measured through this specific thing, which is called embodiment. But then we wanted to measure it even further on. So in the next set of experiments, we equipped our users with the mobile EEG and the headphones, and they were instructed to count the sounds of different heights. So in some cases, the lower or higher, which were very specific, like 5 versus 45, while walking. So that's an oddball task in which we were trying to instruct them to be concentrated about something while also being, mandatory, concentrated to walk somehow. And so what happened in both users is in red and blue, you can see them sitting or walking with our neurocognitive feedback and doing the task. And what you can see there is that they're having a lot of mental layover, a lot of energy nerves that is yet there. So it means that they are using just a part, very small part of their mental budget in order to walk. While in the black lines, you can see then when they are asked to make a mentally difficult thing as those countings, plus to walk, they're over-concentrated, they're using all of their mental budget, and therefore you can easily measure that they are very stressed and not cognitively released. And that's very much important for the rest of the story. So the next task we were doing was to instruct those users for a kind of difficult task for them, what was walking over the stairs. And so on the left, you can see the user with neurofeedback walking quite much quicker, and the mobility is the easiest and most straightforward way to measure the relevance and efficiency of those interventions. And after a lot of analysis, we have learned that it is mainly due to the fact that they are feeling more confident. They're really not losing a lot of mental effort in order to do that. So, and that was also anecdotally reported by themselves. Also, another set of experiments when they were walking with those glasses, blocking their sight, which you can see on the left, and then going over the obstacles, when they were equipped with a full sensory feedback with respect to the commercial prosthesis, they were falling much less over those obstacles. So we are really giving something relevant for their, functional rehabilitation. Then we asked ourselves, why is that all happening? So after some of those trials, we try to understand what do they feel about their prosthesis weight, because users are often saying that they feel prosthesis is too much heavy, even though the modern prostheses are weighting the half weight of the normal leg. So with a proper psychosomatic measurements, we were able to assess that in those trials, when they were having a sensory feedback provided, after those, they would feel the prosthesis and being less heavy than in a case in which they were using a commercial-like prosthesis. And of course, that was connected to the higher embodiment, higher and lower cognitive load, which we secondary measured also in those experiments. Of course, all of these functional benefits are very promising, but no health sanitary system is going to pay for this if we don't have some clinically relevant outcomes. So we're measuring also those. So you can see on the left the level of the pain prior to implantation. Then in pink, you can see the level of the pain, which is almost extinguished while our stimulation was lasting. And then post-explantation, because after 100 days, those patients were explanted, the pain was coming back. So we strongly believe that our pain therapy, the biomimetic stimulation, was able to diminish their pain almost at a level of 0. And that's very important. Also, we've been measuring their metabolic costs. So those users are having 200% higher probability to get a heart attack because they're not confident, therefore not symmetrically walking, and therefore executing much more of oxygen consumption. In our case, when we were providing them the extra confidence, they were able to walk more symmetrically and therefore to have significantly lower consumption of the oxygen. Last but not the least, we ask ourselves, why is this happening? What is the mechanistics behind that? And then in an infinite set of different measurements, we were trying to understand how do they walk over ground, which is an easy task, or over stairs, which is much more difficult task, and how do they reassemble these artificial sensory motor mechanisms. In very oversimplified explanation, what was happening is that they were learning those artificial codes. So for instance, to roll over the leg while walking down over ground, or to use a specific combination of sensors when going up or down the stairs, and therefore augmenting, shaping their walking kinematics much more towards the more physiological way. And that gave us hope that what we are doing has also, mechanistic explanation, and the story is kind of the clear. But then the last but not the least was, as I promised, is what we have learned from those experiments, right? And so then we come up with understanding of upper and lower limb implants worldwide around. What were the common problems and what are the things to solve for tomorrow? And without bothering you with too many details, which are explained in those papers, what we observed also in our study, and we seen as most important thing, is that even though we are able to elicit many good sensations, there are many sensations in white on your right, which are not so nice. Those are electricity-like. So, and those are not exalted in many of those clinical studies and publications. So we want to work on those because we want to eliminate the uncomfortable and ugly sensations for user in order to augment their acceptability. Also, as you could see during our clinical trial, we're having all those uncomfortable cables, which are the reason of why our users have been explanted post 100 days. So we really need expensive but versatile devices, implantable pulse generator, that are going to be able to elicit the stimulation of a proper power consumption and also being able to transmit such a big quantity of information through the skin as it is a biomimetic algorithm. So in order to understand even better those challenges, we were lucky enough to have the histologies of patients that have been implanted post our trial. These were distal sections, and we were able to construct the one-to-one in silico models of behavior of those nerves and try to fit it in on average. So what we learned was that first, we were doing something that is physiologically and physically plausible. And second, we were able to make those 3D implanted nerve reconstruction, which were very much branching. You can see 3 levels in the middle part of the screen. And the situation is not trivial at all, even on such small distances as those we can see. There is a lot of branching, there is a lot of differentiation of size. But what was very much important, we were able to understand that we are quite fitting our previous animal experiments and that we can understand something about this FBR, foraging body reaction changes, and what is that connected to the functional outcomes. More in detail, you can see on the left some of the pictures of what was happening. So we have this fibrotic capsula that has been growing around the nerves, which is around the electrodes, which is also good in some purpose for us because it's fixating those intraneural electrodes. And also we were able to explain the behavior of those during the weeks post-implantation, which was then, this is useful because we can then eventually feed some algorithms that are able to take those into account and counteract against these threshold changes. Not only very specific for the peripheral nervous system, we were able to understand that there are different types of behavior, so different type of perceptual threshold stability, what we call very stable, quasi-stable or variable, or very unstable active sites. The ends are corresponding to the active sites of different implants. And so all of these knowledges are gathering us together to think about the next generation of implantable devices. Last but not the least, we were able to understand also about the stability of sensations. So not all sensations are stable for the same active site from first to the last day. And again, through our specific modeling, we could understand something about the mechanisms. As you can see here, what we hypothesize is happening is that sometimes due to the growth of the capsule over the electrode, after some days, we are not anymore stimulating the closest in front active fascicle, but we are changing the fascicle that we are stimulating. And therefore, it is most probably meaning that we are stimulating other fascicle and therefore the sensation is changing. Therefore, we think that it is not due to the death of cells, which is one hypothesis, or to the central nervous system plasticity, which is also widely discussed. We do believe that it is a mechanistic consequence of the micro behaviors over the small electrodes, and that hasn't been known before. So what's our outlook? What is the lecture we learned for our basic knowledge to push forward? So first problem we had in our clinical trial was that we had very long surgery. So we must make easier electrodes and easier to implant electrodes. Then we have learned that fibrotic answer is important. It's an important issue also, and we have to work on it in order to have more stable devices. And in reality, we are already doing so with our animal collaborators, and we are trying to place some collagens over electrodes, therefore to diminish the fibrotic answer, or at least to stabilize it in a predictable way. And since, as I was showing, we could understand something both about the threshold changes and about the change of type of sensations, and all of those up to date are requiring some user, some expert user that would change the thresholds, that would work on the electroneuron device. We could avoid that in future through the use of, autonomous artificial intelligence algorithms that would take into account that physics and be able to counterbalance those changes over time. So, as promised, diabetics have really important issues connected to the sensory loss. So diabetes is extremely complicated disease in which many of the reasons and behaviors are poorly understood, but oversimplifying what's happening is that we are losing small mechanoreceptors close to the foot skin, and those are therefore not transmitting what we call protective pain. And then what happens is that even a small rock within a shoe could be unperceived, making an injury, and that injury over time could progress into the very dangerous ulcers formation, and then unfortunately many of those are finishing in amputation with a high level of dead exit. At the same time, many of those users are suffering the neuropathic pain, which is similar to the phantom limb pain I've been mentioning before. And present drug medications are often very poor in treating it. So they're stumbling, they're unable to drive the car or to sleep. And then all of those problems are making a way that we have to work on it. We have to propose something alternative. And that's the way, as already shown, that some severe diabetic neuropathy patient is walking. They need assistance. They're very slow and asymmetric. And so we want to work on it with a neuroprosthetic design, which would be similar to the one technology that we've been developing for amputees. So we propose a NeuroLex, and it's an assistance system after diabetic sensory loss. In that system, we're trying to break the vicious cycle. So on one side, we have the progressive diabetic neuropathy, which is in per se pushing those users to have a reduced balance and fear on falls, and due to that, they're having a lower activity and pain. What we want to do is to break that vicious cycle, reducing the pain and increasing the mobility. And to do so, we intend by clinical testing, of course, by the system that's going to have the pressure insole, connected to the brain of the system that is making a stimulation over the purposely designed neurosocks that are going to be able to target the proximal nerve somewhere more proximally with respect to the injury place that is happening close to the mechanoreceptor. As said, that's an ongoing study in collaboration with the Balkris Hospital, and we are using as a first step the quantitative sensory testing to learn more about this system, what is happening to the patient, and then we use our software developed during the years to understand what are the sensations elicited in patients. Yet, even though this idea is kind of interesting and quite straightforward, there are many important scientific challenges to face. So first one is, can we at all elicit the sensations from damaged neuropathic nerves? So the tense in per se, because we're trying to go through the skin, its effects depend highly on this variable positioning of the electrode with respect to the target nerve. And also, we know that sensory restoration is possible when, for instance, the patient is lying down in a very controlled condition as for these MPT studies. And so we do believe it makes sense if we are clever enough to make a proper device to do so, that it is possible, but it must be verified experimentally. Second question is, since this disease is degenerative, how long can we help different severities over time? And what is known is only that this degree is slowly progressive, distal to proximal, with the first sensory symptoms. And so we also know that there is an approximate loss of nerve conduction velocity of 0.5 meters per second per year, and that is somehow connected also what we can measure about a nerve conduction amplitude, which is measured in an indirect way. It's a measure of the density of the fibers close to the foot skin with respect to the duration of the disease. If all of these nonlinear and very complicated informations are captured together, what we do believe is that it's very much possible that we could potentially help those users with assistance over years. And then the last but not the least is, can we reduce that neuropathic pain? So possibly yes. So the gate control theory, which is very well-known theory from 70s, in which, whenever you hit your arm, the first thing you're going to do is to rub the part that you hit it. That's the idea of gate control theory. So the big afferents that we are engaging when we are touching over the area are going up to the spinal cord, and then at that level are blocking the gate of the pain of small nociceptive fiber. And this is basically oversimplified the principle of all spinal cord stimulators or tense stimulators in order to diminish the painful sensation. So they're doing a homeostatic inhibition on a side of area through the paresthesia, and therefore we're stopping to feel the pain. Unfortunately, the present treatment are often having a conflicting results, and we do strongly believe that's due to the fact that they're having a fixed position of electrons in their sizes and a fixed stimulation paradigms, which instead should be personalized and time variant. So what is the idea of the narrow leg design? So we want to target the peroneal nerve, the sural nerve, and the medial tibial nerve. In that way, as you can see here schematically, during the different phases of the walking, we would be able to elicit the areas, for instance, much less selective with respect to the implantable devices, but of course, heel versus forefoot versus dorsum of the leg. And that is possible through the informed in silico design of neurosoc that we did, and together with another side, automatized stimulation. As I promised, it's very important to think about the solution that's going to eventually change the electrode or change the quantity of current that is being injected to the specific electrode with respect to the specific anatomy of the patient, so the trajectory of the nerve or its positioning with respect to the bone, and to the specific severity of disease, or eventually even with respect to the swelling over that day. So if we are able to automatically counterbalance those problems, then we're going to have a versatile device. And so this is very preliminary data in an ongoing clinical study. This is what happened with the patients having a severe neuropathy. So he's unable to feel the forefoot. He's also unable to feel his heel. And also to be sure, during placebo trials, it's not that he is really randomically replying, he's also not feeling anything. Then, when we connect with those electrodes, you can see close to his ankle, the system is what happens. He's able to feel the forefoot or eventually the heel. And again, we're not cheating during placebo trials. He's yet not able to feel a thing. Fortunately, that thing is possible. It's possible for multiple patients. It's working quite properly. And so up to date, we had several patients involved. In all of them, we were able to elicit to some extent, as you can see for two examples there, the lost sensations. And that area is around even quarter of the lost area. And that's very promising. It means that we are able to quantitatively come back with a fourth of lost sensations through the just non-invasive proximal nerve stimulation. And this approach is, of course, depending on the severity and typology of patients, but when connected into the functional walking neuroprosthesis, this is what happened. When all of the kinematic parameters are placed together in a principal component analysis, some participants can be grouped together by a similar walking strategy. And it also happens to be that those are patients with body mass index smaller than 31. And what happens in those patients using this our neural system is that they have improved cadence with more healthier gait. So they're basically taking fewer steps at the same walking speed. And that's, of course, augmented their economy, their efficiency of walking. And we do believe on the long run, that's going to augment their mobility and willingness to go out from house and therefore, to augment, to break that vicious cycle, as it is our goal. And rather than me speaking, it's maybe better to listen to some of the patients.
Ich habe heute diese Tests gemacht, mit und ohne Stimulation zu laufen. Und ich muss sagen, das gerade Auslaufen, das einfach eine gerade Auslaufen, was mir schwer fällt, weil ich immer so die Beine so ein bisschen unkoordiniert bewege, ist mir mit der Stimulation viel leichter gefallen. Ich habe auch das Gefühl, ich bin viel gerader gegangen. Ich kann es nicht erklären, warum.
And I just jumped this, but also up-to-date tested patients with a pain, that pain was clinically relevantly diminished. So over 30%, 35% diminished. So in a small wrap-up, we're developing the neurotechnologies through the hypothesis-driven modeling approach rather than trial and error. And therefore, we do believe that we are propelling the quicker clinical transitions. So how do we do that? We start from in vivo experiments in animal and humans, and we are proposing in silico receptors and nerves that are iteratively validated and used for the future tuning. Then we do the physiologically plausible conveying of sensations to the human body, both invasively and non-invasively, through use of this accumulated knowledge. And then we are able to do these translational discoveries about less pain, more confidence, mobility, or which at the end would drive through the healthier life and social reintegration. And that, to my belief, is that it's going to promise us for tomorrow's generation the healthier aging and more meaningful life, which is the biggest goal of the assistive medical devices. Here is probably one of the two most important slides, is that the pivotal importance of this is the translational collaboration. And sorry for so many things, it's so busy slide, but these are the persons behind, all of these clinical trials. Here specifically, I've been mostly speaking about left upper level, which is Unispital and Balkris clinical collaborators. But we are working with all of those beautiful persons. And very importantly, we are taking into account very, very at this stage of the human kind, the ethics, and we are thinking about what we are doing and how are we neuromodulating those nerves in a proper way. That's super important. And of course, these are the persons that did this work. So this is the most important slide. These are the super clever and talented young researchers working together with me and making this extraordinary work with a lot of passion and a lot of smile all the time. And with this, I have to thank many of the European funding commissions and Swiss funding commission, and I'm more than happy to take any question. Thank you very much.
Thank you, Stanisa. This is a most fascinating presentation. And as you mentioned, this has real life relevance. I mean, improving the quality of life for so many people. This will make such a difference to just being able to walk independently and being able to walk without feeling that you might fall any moment can make such a difference to everyday behavior. That's the most fascinating. There are already some questions coming in. I'm not sure if you can see them. here because they are a bit scattered. There's someone right at the beginning of your talk was asking about, can you quell spasticity consequent brain injury?
Sorry, so I didn't very well. So can we work with spasticity? Is that the question?
Right, are you able to quell spasticity? Oof, that was a question right at the very start of your lecture.
Yeah, okay, great. Very difficult question. Honestly, we are working with the patients that are also having spasticity, but the question is difficult in that set because we are having trouble. So in a first set of a clinical experimentation, it's better to avoid it because there are already too many problems in per se already. And with the spasticity added on top of it, it's not an easy thing. We had some patients with spasticity, and we are trying yet to disentangle up to which level are we able to help. And so by the moment, the answer is we do not know, but it is something that we are absolutely taking into account.
One attendee tries to combine lecture 1 and lecture 2 of today, suggesting maybe you could use Silktrodes instead of the normal electrodes in your large muscles, because you mentioned that you were worried that maybe the electrodes don't last.
Yeah, so yeah, that's a great proposal, but electrodes, so yeah, indeed, our long-term vision and dream is to use more sophisticated electrodes and even to more optogenetics. But this is a great question because it's always a trade-off between what we can achieve between today and 5 years or in 50 years. So I do believe that a generation of maybe ourselves or our children would benefit of some of these newest technologies, but unfortunately at this stage only the polyamide silicon electric electrodes are the ones that have some certification and are usable in humans. So we wanted to do with all of its limitations what is possible with the presently existing electrodes, and this is how far did we arrive. By the way, those electrodes are quite stable, and there are other cuff electrodes that are even more stable, and their stability is engaged even up to 8 years in humans in Sweden or also in Cleveland, in Case Western. So the stability was not the main problem. The main problem in our clinical trial that I've been explaining was the fact that those electrodes are so tiny and we had these big cables going transcutaneously, so it was super easy to pull them out. So it's more the fixation than the electrodes in per se.
Here's a question about the intensity. With this nerve-machine interface, does the intensity of the sensory stimulation scale with the intensity of the force generated with each step? Or is it like a set intensity?
That's simply a great question. Yeah. So in our papers, if you read them, it's very well described. And so we also tested both options in reality. And in our papers, in our clinical study, we mainly used the proportional intensity. So it would be really proportional to the force that is being measured. But of course, that's a clever question because one can think that our walking is pretty much, a state action and it's depending on transition. So we also tested this, and some of those results are going to be published very soon. But in a nutshell, it's a little bit better to use the proportional way of encoding.
Someone is interested in how long do these neuroprostheses last?
Yeah, I've been mentioning this. So these neuroprostheses, as was mentioned in a previous lecture brilliantly, are super complex devices. So you have a neural implant, which is just a piece of that device. There are many other things. So there are the cables that nobody ever speaks about. And those cables are tricky. They have to pass through the human body. And then they have to go to some system that is injecting the current and energy into the human body together with information, right? And then you have an external part of the system that is speaking, like controllers and all of the data integrity. All of these components are to be taken into account when we speak about the longevity, right? And so it's a super complex question. On the side of electrodes in per se, in peripheral nervous system, as I've been mentioning, similar implants, which are usable up to similar extent, so the cuff electrodes have been in users already about decades. So it's a very promising status for electrodes. We yet do not have, to the best of my knowledge, the full implantable system. So the implantable pulse generators that are under the skin for multiple years, both because that's an a quite tricky engineeristic project, and also because it's a financially heavy project. Recently in United States, the DARPA was financing the big effort with the multiple American centers to develop a fully implantable solutions within a haptics project, and very close to have it. So, and I think also Medtronic was involved. So I think many of those technological problems are about to be solved back to the angle. And so I believe we are there, we are almost there. So that longevity in per se could be measured in a five or half decades already. That's my feeling.
Okay, yeah. This is now a follow-up question from myself. Every chain is as strong as the weakest link. So at the moment, you mentioned all these different components. What do you think, what is the weakest link?
That's a very difficult question and a very good question. I would, unfortunately, tell that there are always few weaker links, right? Nerve interface, nerve electrode interface is in per se critical link, and it will remain for a while critical link, because you always have to make an extraordinary attention there. But there are some links that we never have tested yet. So for instance, when you make you place implantable pulse generator close to the nervous system, the temperature is an issue, right? And so if you increase, let's speak about the brain just to generalize. I know that Neuralinks is doing a great job, and they're suffering, to best of my knowledge, a lot about how to control the temperature in a proper way, so not to burn the pieces of the brain. And you would never think about that, but those are really tricky questions. And there are several as those, like the electrode nerve interface, or implantable pulse generator temperature and capacity, and or in per se also the data capacity, because we have to stream so much of information through the skin that at the end, a priori, I do not know how much stable is it while we do not have those systems ready.
Yeah. There's a question here. Have you ever been able to test patients with Parkinson's disease?
Great questions. Indeed, there are studies from Romulo Fuentes and Nicolelis about usages of different type of stimulation, epidural or peripheral, also for the Parkinson's disease. And I think that's a promising venue, if not at least combined with other types of stimulation. Unfortunately, in our small group, we were not yet able to do it, but we're more than happy to be in those types of studies. Very recently, they showed very promising results with epidural stimulation and a Parkinson's disease in APFL Lausanne. So I think that's the way to go, certainly in combination with the drugs in future or something similar.
Someone wants to know, how long does it take until the NeuroLegs will be on the market?
Oh, that's a great question. So NeuroLegs, I suppose speaking about the diabetic example, right? Because the first implantable device is in a spin-off phase with a great team of persons working behind of it, and they got even FDA breakthrough approval to get this device on the market. While the diabetic device, we are yet into the clinical study, but there are very much engaged younger persons who want to spin off that technology. And so also I think that's the best philosophy. Work in research until we don't get a reliable proof of concept and engage a lot of public money to get some really good science, and then it must be pushed out. And so I think in 3 to 5 years, we can speak about non-invasive device here, there around, because I know there is a lot of interest.
The last question here is, have you ever worked on intraspinal cord stimulation to restore walking? Is it a better way than the transcutaneous methods?
Intraspinal stimulation is one of ways. There are many different. There are persons working intraspinally, like Viviane Mouchavar is the world expert from. She's in Canada, and she's admirable professor with great insights in that area. There are other groups working with an epidural spinal stimulation, and those. And of course, there are guys from Pittsburgh working also on epidural stimulation for the sensory feedback. So there are many great groups doing those different efforts, complementary efforts. I think they're all valuable in a proper way. depending on a type of injury and type of patient we have on the disposal. For that type of technology, I would really tell that it's really for the spinal cord injury, and they have very, very promising results. I think they're even close to the clinical trial, but don't take me for the word. And epidural spinal cord stimulation has been used extensively in clinical trials for the movement restoration. Maybe the future is combining the periphery with epidural stimulation. That would be my 5 cents regarding that.
Yeah, thank you very much. Thank you for a fascinating talk. We are now here at the interface between basic science and clinical application, what we usually call translation. You are just sitting there at the right moment. So yeah, I think everyone can agree with me that we should give Stanisa a good clapping, and thank you very much for a most fascinating talk.
Thank you for this great opportunity.
So now we are coming to our last speaker of today, and this is Carola Haas. She is experimental epilepsy research, and this takes part in the Department of Neurosurgery at the University of Freiburg. And the title of her talk is Low-frequency stimulation successfully interferes with focal epileptic seizures without affecting hippocampal function. And I think that the last part of the sentence is quite important in this context. So, Carola, it's all yours.
Yeah, hello everybody. It's a pleasure for me to be here, and I'm very delighted to be invited to this really wonderful symposium. And my topic actually was already introduced at the end of the last speaker. Actually, I have problems to see, so I don't see anybody. Do you see my screen still? No.
We can see your screen. We can hear you well.
Okay, so I just tried again. Okay, so I continue. So in the last talk, neuromodulation was the topic, and it was also the topic basically of the whole meeting so far. And we heard a lot about the possibility to interfere with nerve function or stimulate nerve function with different devices. And my topic actually is very much related to that. So we have heard that there is, in particular, like in the last talk, there's neuromodulation performed in spinal cord or peripheral nerve stimulation to cure neuropathic pain, but also chronic migraine in the CNS, and spinal cord injury was a topic. And also movement disorders were addressed, so like morbus Parkinson, which is the gold standard for deep brain stimulation. And deep brain stimulation is also applied in intractable depression, obsessive compulsive disorder, and in intractable epilepsy. And this is my topic, and it has a very strong translational goal to treat epilepsy. So epilepsy is not one particular disorder, it's a group of neurological disorders characterized by recurrent epileptic seizures. This has a high prevalence. 50 million people are affected of the world population, and this is a lot. It's 1%. Many can be treated by medication, but there is a high proportion of pharmacoresistance among these patients. Epilepsy can be generalized or focal. It is shown here, so it either arises from a certain area in the brain and staying in the area, in this area, or it's affecting the whole brain. Then it's generalized. And as I mentioned in the beginning, because it's a syndrome caused by many underlying problems. So here you have a cartoon just giving the idea how many different reasons can cause epilepsy, but they all end in the same symptom in seizures. I'm interested in one particular type of epilepsy. It's called mesial temporal lobe epilepsy, and it's the most frequent type of epilepsy in adults. Here you see an EEG recording with several electrodes, and you can easily see that one area, this is originating from the temporal lobe, gives rise to the epileptic activity. We see a pathology in these patients in many cases. So here you see an MR picture of a patient, and one side, the hippocampus, is increased in the T2 signal, and it's smaller, it's atrophic. When we look at this hippocampus in a histological staining after removal, surgical removal, then you see that the normal hippocampus has it nice layering of neurons. We call that the cornu ammonis and the dentate gyrus. And in the case of the epileptic patient, there's severe cell death and in different areas, which causes sort of this shrinkage of the hippocampus. And we also see structural changes in the dentate gyrus. So epilepsy is treatable, in this case the MTLE, by anti-epileptic drugs, so AEDs. But the AEDs have disadvantages like they lack spatial control, have side effects, and often they end up in pharmacoresistant after the treatment, or they don't work at all from the beginning. In these cases, resective surgery is one option. So that means that if the hippocampus or the temporal lobe is affected, it can be removed, and often the seizures are alleviated. But it has certainly side effects like loss of function in this area, and often it's not feasible in the patients because multiple areas are affected, or eloquent areas which cannot be removed. So one really helpful option is deep brain stimulation. And it's has the advantage of being reversible and adjustable. It has high spatial and temporal precision, but it also has side effects, and there are non-responders, so people who don't respond to stimulation. So there is a need for improvement, as always. What type of stimulation is used for the treatment of MTLE? So far, high-frequency stimulation is in use, even in an open loop or closed loop fashion. And the RNS system, which is produced by NeuroPace, is so far used only in the United States. It causes seizure reduction and on quality of life improvement. But the disadvantages is that it has many false positive detections and side effects, as always. And the efficacy depends very much on the target. And here the MTLE comes into play because it's not a good target. So we were thinking, are there other possibilities of using high frequency stimulation, and can we work along this line? And we chose low frequency stimulation. It's so far only used in rare cases in humans. There are very few data available, but it has advantages like less electric current injection. Then it's more naturalistic, and it decreases excitability. And we wanted, or our aim was and is, to try to develop low frequency stimulation for the treatment of MTE with severe hippocampal sclerosis. One has to know that in humans, an initial precipitating injury in early childhood can be the trigger for the development of MTLE in the adult situation. And the process between this insult and the seizure onset can usually last many, many years. It's called epileptogenesis, and it includes the development of the pathology which I alluded before. So our approach is and was that we try, or not we try, we mimic the disease in animals, in mice, and then we study different aspects to understand the origin of the paroxysmal activity, the epileptogenesis, and now finally in the last our last sort of emphasis was lying on developing parameters for treatment, stimulation treatment. So the advantage of this mouse model is that we, in contrast to the human situation, we can recapitulate the major hallmarks of the disease. So the seizures on the one hand, but also the pathology on the other hand, in a defined time scale. So I would like to give you a quick overview for what we sort of reached with this model already, the success we had by using it. And our interest was to study the process of epileptogenesis in a longitudinal manner. So not only to induce the disease and then do cuttings at different time points and investigate the pathology or whatever. So we choose MR imaging, which has the advantage of being able to do it in a longitudinal way. So we did it in different modalities. So T2 weighted imaging and diffusion weighted imaging, and also spectroscopy. And at the end, we did a retrospective correlation of the results of the imaging with, on the one hand, with activity, but also with the cellular changes. And the idea was, could we identify biomarkers to sort of give the advantage for, certainly always with a translational idea, to detect the disease at an early stage and not in the final stage when it has developed fully. So what we found when we did this, here you see T2 weighted imaging series, and you see that the contrast is changing over time. And what we could find was that the strongest changes in the imaging, T2 imaging, was in the initial stage, so very early after the status epilepticus insult, and that this correlated, these early changes correlated very much with the degree of cell death in the chronic stage. And at the same time, when we did spectroscopy, we could see that the early and permanent loss of glutamate is predictive for the degree of hippocampal sclerosis at the end or in later stages. So this was already an interesting finding. And when we looked at the diffusion-weighted imaging, which is gives a picture of the structural reorganization in the tissue, and here you see the different colors correspond to different directions of diffusion, and so you can easily appreciate here that in this area, which we know it's the dentate gyrus, we have the strongest changes in diffusivity over time. So this was the second marker we found, in a way, that the progressive increase in the dorsoventral diffusivity in this direction is predictive for the structural changes in the dentate gyrus. So we were successful with developing biomarkers here in the preclinical level, but it didn't tell us anything yet about the structural changes on the synaptic level. And this is what we needed if we wanted to decide which structures can we target to develop an optimized stimulation protocol for the treatment of the epileptic activity. And here you see a scheme of the hippocampus for the people who are not familiar with, and I guess there are some. So medial entorhinal cortex gives rise to the main input fiber system into the dentate gyrus, and terminates on one particular cell type, which are the granulocells. And then the information is processed further in the other hippocampal areas from CA3 to CA1 and then exiting again. So this is a well-known presynaptic pathway. And we wanted to know, is this pathway maintained during the epileptogenesis? And can we target, what structures can we target? And here we used transgenic mouse line, which is green, so gives the option that we see granulocells in green, and then we did anterograde tracing, which allows us to label the incoming peripheral path, and here you see that the peripheral path is terminating in a layer-specific way here on the dentate dendrites on the dentate granulocells. And then we did 3-dimensional reconstruction of confocal microscopy. And then we could easily identify the pre- and the postsynaptic target. And it gave us the information if synapses were newly formed and where. So these are dendritic spines, these green structures, and then the red targets here are the fibers, the presynaptic part. So this was a healthy situation, and actually this was all done by Philipp Jans, a very talented PhD student in the lab. And when he did this 3-dimensional reconstruction and compared the healthy situation with the diseased situation, then he found that on the one hand, this was very surprising for us that the peripheral path input was maintained in the epileptic situation. And he also found that the synapses were massively increased. So that meant that the connection between the incoming fibers and the surviving granule cells were very much strengthened. So new synapses were formed. And when we now look at this new epileptic circuitry, then we could sort of paint a new picture in comparison to the situation, the healthy animal. We see that the incoming fiber system of the entorhinal cortex is still intact in terminates on the granule cells, but we see also a lot of cell death, which I showed you already in the beginning, which is part of the pathology. And so when we were thinking about stimulation targets, we decided that the granule cells would be optimal because they are still there, and the strengthening of the connection was increased via increasing synapse numbers. So that's what we did in the next step. So we used what we call an opto-inspired identification of target cells for brain stimulation. So what we now used was our knowledge of the peripheral path and its longevity in this situation. So we injected AAV viruses carrying generodopsin and at the same time kainate to induce the hippocampal seizures. And at the same time, or a little later actually, we implanted optic fibers and wire electrodes, and then we could stimulate and simultaneously record to see the effect of our optogenetic, in this case, low frequency stimulation. And here you see the cellular responses of hippocampal dentate granule cells upon stimulation. And for the readout of the epileptic activity, we used a machine learning algorithm, which helped us a lot to in an automatic way classify the epileptic form of activity. And this was done in collaboration with Katharina Heining, who developed this algorithm, and it distinguishes 3 types of different bursts. So we have high load bursts, so that means this is really very strongly increased neuronal activity and clusters of this, and then lower load, medium load and low load bursts. And then we started our actual experiment asking the question, does the optogenetic low-frequency stimulation interfere with spontaneous epileptic activity? This is an experimental design, which I explained already, and this was performed by my PhD student, Enya Paschen. So here you see on the left side, you see the pre-recording, so without stimulation, and you can easily appreciate that there are strong clusters of bursts, so reflecting the epileptic activity, ipsi and contralateral in both hippocampi. And then when Enya started the low frequency stimulation, then you see that this bursting completely disappears. And this is here seen in the quantification, meaning that from the pre to the stimulated time point, we see a massive drop of activity to almost nothing, followed by an increase again post-recording. And this effect was also on the other side, in the other hippocampus, which was not stimulated, seen. So that was very promising that we could actually with this low 1 Hertz frequency prevent seizure generation. And certainly we continued along this line, and we wanted to certainly now go in a translational direction, and that means that we have to go away from the optogenetics, because this is something we cannot do in patients. So we want to transfer our cell-specific stimulation to a region-specific stimulation. And so what Enya did was first that she tested if still with optogenetics, if she could elicit, and we knew that it is possible to elicit a generalized seizure in this case with 10 Hertz pulses. But in this case, she did a preceding treatment with the 1 Hertz stimulation. And what she saw was that also provoked seizures could be even prevented by the stimulation. So it's a preconditioning possibility that the 1 Hertz pulses hinder sort of seizures to occur. And now we switch to electric stimulation, because we wanted, as I said already, to go into a translational direction, which is not feasible with optogenetics. So with the electrical stimulation, she got the same result. So we can say that the timing is here very important, and preceding low frequency stimulation, as I said, prevents those seizures. So next question was certainly, is this effect repeatable? Can we maintain the efficacy? And to this end, we did Enya actually did experiment lasting over weeks with repeated sessions of stimulation intermingled with reference recordings, and then stimulation sessions again. And when she did that, here you see again the pre-recording, week 5, week 6. So the epilepsy comes back. But the suppressing effect was maintained over weeks. So this is very important, that we don't get a desensitization of the system. And certainly we wanted to know, is this effect also can be applied not only for 1 hour, but for longer. And so she tested several hours, and that was similarly effective. And last but not least, what we wanted to see if there is also discontinuous stimulation effective, so that we don't have to stimulate 1 Hertz continuously. And when she did that, you see here the confetti plot with a lot of epileptic activity. And when she applied the discontinuous stimulation with 10 minutes on and 10 minutes off, then she got a very stable suppression of activity, even with the breaks of 10 minutes. So what I told you so far is certainly interesting, but we were very much interested what could be the mechanism. And to that, to answer this question, we collaborated with Marlene Barth's group in the physiology department, and produced, following the same experimental paradigm, doing kinase injection and peripheral path channel rhodopsin expression by virus injection. Then we produced, in the chronic situation, we produced acute slices, and here you see granule cells and the peripheral path fibers here crossing. And following stimulation of the peripheral path now in vitro in the slice, we saw on the individual granule cell responses, we saw a strong decrease following OLFS over time. So that means 10-minute stimulation, as we had applied previously in the discontinuous way in vivo, was enough to decrease the excitability of granule cells. And similar results we got with increasing stimulation intensity. We got a reduction of the discharge probability of the neurons. So this is a hint how the 1 Hz stimulation works. So it reduces the granule cell discharge probability, but the intrinsic properties are not altered. I didn't show these data for reasons of time of the intrinsic properties. So our next goal was, can we apply the stimulation in a closed loop fashion? So this would be very desirable to be applied in humans, so that here the activity is constantly, the brain activity is constantly measured and fed into an acquisition system which evaluates the seizures threshold, which we set to 13 spikes in 10 seconds. And if this threshold was reached, then stimulation was performed at 1 Hz for 10 minutes. And this was sort of applied now, this closed loop system. And certainly the system used an online algorithm, which I described before, to detect the epileptic spike rate. And when we applied now this algorithm, this closed loop system, that you see that this is what happens in the reference recording, a lot of epileptic spike activity going on. And then when the on-demand LFS was started, then the spikes were reduced to strong degree. And this is what we can see here in the quantification, that in particular, the high load bursts, this is the yellow, the trace here, the yellow clusters, that they are the ones which are predominantly reduced. So that means that our system works, the closed loop system works, and the next step was to compare it now. What is the efficacy of the closed loop system in comparison to the open loop system? And that what was done by Enya in collaboration with a master student. So in the same animal, the different simulation paradigms were applied and compared in their efficacy. So, and what we found was, and that was very nice to see, that the discontinuous LFS, that means 10 minutes on, 10 minutes off, was to some degree efficient, but not as strongly as the on-demand closed loop or the continuous one. So the best comparable simulation paradigm, so to speak, is the continuous and on-demand. So that was very exciting. So now the question, I would like sort of to summarize what I showed you in so far, that when we stimulate the sclerotic hippocampus with low frequency, then we get a repeated prevention of spontaneous focal or also evoked generalized seizures. And now we can say that it's most likely mediated by a lowering of the responsiveness of granule cells. And we also found that on-demand LFS is similarly effective as continuous LFS. And now the last question, or most important question is, does this stimulation affect cognitive performance? Because if we want to go to patients, then certainly we don't want to impair cognition with our stimulation, because epilepsy patients already suffer from cognitive problems. So we want to avoid this. And to this end, I have to sort of also to emphasize how important the hippocampus and the entorhinal cortex are for navigation, learning, and memory. And especially the dentate gyrus is involved in several mnemonic functions like pattern separation, completion, and novelty detection. So it's absolutely important brain structure for our everyday life. So this is something which now is the second part of my talk, and the last part where we investigated on the behavioral level mobility, anxiety, navigation, learning, and memory in mice after low frequency stimulation. How was this done? So again, we are still in mice. So again, Enya, she performed following kinase injections, implantation of electrodes, which allows then the recordings of local field potentials, and certainly of the electrode for stimulation, followed by behavioral tests of different kinds. So we performed object, location, memory tests, light dark box test, Barnes maze, and novel object recognition, which are almost either anxiety tests or memory tests. I will not show you all the data, but only selected ones for reasons of time. So the light dark box is a test for anxiety, and you see here on the left side that control mice injected with saline, they explore the arena very frequently, and they don't hide in the dark box. So they go into the open, but this is not the case for kainate mice. So they are much more anxious. And when Enya compared mice which had been stimulated with LFS in both experimental groups, then she saw that there was no effect of the stimulation on the going out into the arena. What we see is what I said already, that the kainate mice are much more anxious, which is reflected here, but they are not, the anxiety is not increased by stimulation, which is also very important. So in the next test, it's a relatively complicated test which needs a lot of training for the mice. They are set on a arena with many holes, and because they don't like the light which is shined on them, they try to hide. And then they have one escape box where they can hide. And during the training, they learn very quickly, as you can see here, within 5 days to find the hole and to hide. And as you can see, all the groups, saline ones and the kainate ones, and stimulated and not stimulated, they all learned the kainate a little less, and they also found the target. So one can say that the learning as such was not affected by the stimulation, which is also very important, that the mice can learn. And then certainly the mice use different strategies how they find. So this is the find they hold, and this is spatial navigation. Yeah, they have cues and they follow their cues, and which is a strong hippocampal function, and they learn also this spatial navigation during the training. And here you can easily recognize that epileptic mice use a different strategy. So they don't have a good spatial navigation as such, because they just run from hole to hole until they find the escape box. And the stimulation did not significantly change the search strategy in both groups. So the stimulation which we use does not influence the search strategy in a spatial memory task. And finally, the recall is very important hippocampal function, that you remember where you are, not only that you store these memories, but also that you can recall them. And this is sort of tested in the test situation after 5 days of training. And what we easily can see is that epileptic animals are much worse in their performance. So the recall is less successful, but stimulation does not worsen the recall. So we cannot change it, which is a pity. Yeah, we would have liked to increase the memory performance. If that would have worked, then we would have been very happy, but it doesn't interfere with the memory performance, and this is already a good news for us. So I would like to conclude that our mice, the stimulated mice, have a similar anxiety level as unstimulated littermates. So anxiety is not increased by this stimulation paradigm. LFS does not interfere with spatial navigation, and LFS does not interfere with memory formation or recall, which is good news for us. So that altogether, what I showed you today, we think that these findings are very encouraging to be translated to the human situation, to be tested in humans for seizure control in one of the most common forms of drug-resistant epilepsies. And we are already in contact with our neurosurgeons here, in the surgeons in the neurocenter, and also in other places in Europe, which are willing to test our stimulation protocol for MTLE patients. And with that, I would like to thank my funding agencies and all the collaborators and the students who performed this study. Thank you for your attention.
Thank you very much for this presentation. This gives us so much promise. At the moment, this is still in the preclinical stage, but everyone who has ever been working in neurology can see that this has an enormous potential in the future. And I'm really happy to hear that you are already collaborating with the people in the clinic and trying to really do the step from an animal experiment to something that may be beneficial to patients. I was also impressed the amount of different techniques that you're using. You have to be good at behavioral neuroscience. You have to be good at electrophysiology. You have to know your pharmacology, your histology. You're using optogenetics. You have to use computers to develop these sophisticated algorithms. That's quite a wide range of technologies that you have to have in-house and in your group.
Thank you. Yes.
There's a question coming in here from Camilo. A question that is probably concerning the middle part of your talk. How did you cross-validate your machine learning-based model?
Cross-validate. I'm not sure if I understand this correctly. Certainly, we always, okay, the first thing is that it's sort of the result of the algorithm is always tested by visual inspection, yeah? That the people who work with these LFP recordings, they not only trust the algorithm, but they always have a look at the recordings as such and check if it can be true what the algorithm says. I hope that answers the question.
Yeah, well, the participant can get back to you if he wants. There's another question. Someone is getting already a bit anxious that this might start soon. So the question is, it's made of two parts. When might these human trials start? And the second part, digging a little deeper, how exactly would you do the stimulation? Is this done with a cap or has it to be more invasive?
Okay, good question. Okay, certainly we cannot go with our stimulation paradigm to the clinicians and say, now test it immediately. Yeah, certainly we need an ethics approval, so that the ethics commission of the hospital allows that we can do this, and certainly we have to follow certain rules with pre-tests and so on. And the first idea is that we use patients which are implanted already. I mean, there is regular implantation of Dept electrodes in patients where the seizure focus has to be found. Yeah, because often the seizure focus is not obvious. Yeah, with this surface electrode. So then these patients are implanted for a certain period of time to define the seizure focus, which then can be operated or resected later. And this would be the first step that we try with these transiently implanted patients, that they can get this stimulation for a short period of time. And then we see if it's successful or not.
Okay, thank you.
Yeah. And then certainly, this was already alluded to by the previous speaker. He started with 3 patients, yeah, as a sort of a clinical trial before it can be applied in large patient groups. And this is something we have to do certainly as well. Yeah, I mean, there are strict regulations in the FDA as well as here in Europe, how we have to continue if we want to go from an animal experiment to humans. There are very strict rules. Yeah.
I mean, this has ethical implications. That's the normal way. Fully agree with that. Just a few questions for general understanding. You were using the terms high frequency and low frequency stimulation. Can you give us an idea of what frequencies we are talking about?
Okay, the low frequency which I showed was 1 Hertz. Yeah, and we also tested lower ones and higher ones. So that's we didn't just start with 1 Hertz. But the higher frequencies, which are used also for treatment of Parkinson and other syndromes, as I started out today, are in the range of 100 Hertz.
Okay, yeah, so that's quite a difference.
Yeah. And that's something I wanted to ask the previous speaker, because he didn't talk about his stimulation frequencies at all. Yeah, what frequencies does he use to get this improvement of sensation? What he showed, what was absolutely fantastic. Yeah, that I would have liked to know.
I can get you in touch with him. We've got all his coordinates. So if you want to have a private interaction, please feel free to do so.
Zürich is close. Yeah.
Yeah. This is a question of mine. I've been working on glutamate receptors a long time ago. You mentioned that the symptoms are stronger when there is a strong loss of glutamate at the very early stage. Tell me, is this related just to the epileptic seizure itself, to this enormous burst of activity, or is there anything else involved?
I mean, we have a strong, okay, there's certainly in the very beginning, in the first hours, there's a massive glutamate release, so that a lot of synapses are depleted, I guess. And then second, there is also traumatic cell loss. Yeah, so that nerve cells are dying, synapses are dying, and this contributes altogether.
So here's a question from Harry McGee. Stress can sometimes trigger temporal lobe epilepsy. In your AI detection of seizure activity, did you notice an association with stress?
No. But I think that's difficult to transfer from, I mean, stress, he means humans, I guess, certainly. And in our animals, I think we cannot observe this.
Okay. In the meantime, there comes a response from the earlier questionnaire. You remember the person who asked about cross-validation. He says, by cross-validation, I meant assessing how the results of a statistical analysis will generalize to an independent data set.
Oh my God, that's a difficult question. Maybe I can answer this by saying that certainly we analyze long periods so that we have a lot of the algorithm detects works over long periods of time, and then certainly we have also many animals and many sessions, which gives us then an idea if that what we see is statistically significant.
Yeah. Yeah, so thank you very much. Oh, by the way, the last questionnaire also added, I loved your talk. And I think we can all agree with that. This was a beautiful session. There's no more questions now. And I would like to extend my thanks to the other speakers as well. Some of them may have logged off already because it's getting late. But this was a very, very helpful session. And we have learned quite a lot. We have learned quite a lot about the interface from preclinical studies where you do very detailed analysis of animal experiments and how we carefully then can translates them into bedside help for patients in need. So with this, we come to a conclusion. Thank you, everyone. And I think a round of applause is probably appropriate at that stage. So bye-bye, everyone.
Bye-bye.